MS platform. Students, hello.
Sir, which PPT or PDF you're talking about?
The PPT for the first lecture, for the second lecture, about the coherent sources, the phenomena of interference in thin films. In reflected light case and in transmitted light case. Have you gone through the contents? Have you gone through the e-tutorial which are uploaded?
Sir, I was not able to understand the thin films part.
Okay, I am explain. I will we will discuss that thing in today's lecture. So, students, in previous lecture we have discussed about interference phenomena and what are and this we have also discussed that any two independent sources of light cannot be coherent due to the phase difference, due to the difference of the phase, because they are not able to maintain a constant phase difference between them, and that is why they are incoherent. So, in order to obtain interference phenomena, interference pattern in real life, in practical life, what we do, we obtain two virtual sources from a single real source. So, let me share my screen. Is the screen is visible to all of you? Hello.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So we have discussed about coherent sources. Coherent sources are those sources which have same frequency and which maintain a constant phase difference between them with respect to time and space. So, and as we know that two independent light sources cannot be coherent, and that is why we obtain we obtain two virtual sources from a single source of light. And there are various methods for generating coherent sources. And these are Young's double slit experiment, Fresnel biprism, Michelson interferometer, and Newton's rings. And this is showing the interference pattern. As we have discussed in a previous lecture, that in interference pattern, we obtain maxima for even multiple of pi. So you can see from this pattern, you can see that you are getting maximum intensity for 2 pi, 4 pi, 6 pi, and you are getting minimum intensity for pi, 3 pi, 5 pi, or minus pi, minus 3 pi, minus 5 pi. Okay, so this we have discussed that if we constructive interference will be obtained at those points at which the phase difference between the two interfering light waves will be even multiple of pi, or the path difference between the two interfering waves will be even multiple of half wavelength. So these are some of the techniques by which we obtain two virtual sources of light, two virtual coherent sources of light, originally originated from a single real source of light. So these are the different conditions for obtaining sustained interference pattern. The first condition, you know that the interfering sources should be coherent sources. They should be of monochromatic light. We should use this. They should be of single frequency. That's why they will call be as monochromatic. Wavefront must be in similar state of polarization. Means if they are plane polarized, if one of the source is plane polarized, then all the interfering sources should be plane polarized. If they are circularly polarized, then all of the sources should be circularly, and if they are elliptically polarized, then all of the sources should be elliptically polarized. Source separation must be very small. Source screen distance must be very large, and the amplitudes of the interfering waves must be ideally same, almost equal. The amplitudes of the interfering waves should be almost equal, because if they will be almost equal, then at the points of maximum intensity you will be you will get an intensity which will be greater than the sum of the individual intensities, and at the point of minimum intensity you will be getting almost zero brightness. So the contrast of the brightest fringe and the darkest fringe will be large. Source slits must be narrow. The sources and the slits should be as small as possible. And so these are the different conditions for observing sustained interference pattern. Methods, as I have already discussed with you, that in real life, two independent sources cannot be coherent. That is why by using these two methods, we obtain coherent sources of light from two virtual coherent sources of light from a single source of light. And these methods are wavefront division and amplitude division, or you can say division of wavefront and division of amplitude. As you have read about this experiment, Young's double slit experiment. Let me discuss in uh, bigger diagram. This diagram, you can see that in Young's double slit experiment, there is a light source, there is a broad source of light, and at two equal distances from the light source, we have two slits, or you can say two pinholes. So you know that as how Huygens has described the light source, Huygens has described the light source as a source of disturbance. And he had said about the light source that from the light source, disturbances are created in all directions isotropically, uniformly in all directions. But since we are only concerned with the wave fronts which are generated in the forward direction, that's why we have shown the wave fronts in the forward direction only. So what are wave fronts? You know that since S is a light source, so what it will do? It will disturb. It will produce disturbance, and this disturbance will disturb all the particles in the neighborhood of the light source. And you know that if you join all those points which are at the same state of vibration, which are at the same position, or which are at the same distance from the mean position, from their mean position of vibrations, then what you get? You get the wave front. So wave front is the locus of all those points which are vibrating in the same phase. So if we have, suppose that we have a spherical light source, therefore the wave front will be of spherical shape. If the light source is of cylindrical shape, then the wave front will be of cylindrical shape. And you know that plane wavefront is the approximate case of spherical or cylindrical wavefront. If we are at a very large distance from the source, then a very small portion of the spherical wavefront or of a cylindrical wavefront can be treated as a plane wavefront. For example, if we are only observing a very small portion of a spherical wavefront, then we can say that it is a plane wavefront. So this is a light source, spherical. Since it is of spherical shape, therefore spherical wavefront will be originated, and at the pinholes S1 and S2, from this primary wavefront, secondary wavefronts will be produced. Or and in another words, you can say that some portion of the wavefront which is originated from the actual light source S will pass through the slit S1 and some portion will pass through the slit S2. So you can say in this example, wave front is divided. Some portion of the wave front is passing through the slit S1 and some portion is passing through the slit S2. And then these S1 and S2, these two pinholes now behaves as a secondary source of light. You know that Huygens has described that each and every point, from each and every point of the wavefront, secondary sources of light can be originated, and those points he has denoted as a secondary wavelet. Huygens has given each and every point of the wavefront as the secondary wavelets or secondary sources of light. So secondary wavefronts will be originated, wavelets will be originated from the pinhole S1 and S2, or you can say from the slits S1 and S2, and then in the forward direction they will interfere according to their phase difference, and on the screen you will be getting alternate dark and bright fringes. It will depend on the property of the light source. If it will be a monochromatic light source, then you will be getting a alternate dark and bright fringes. If it will be a light source, if it will be a white light source, then on the screen you will be getting a colored fringe. So you know that in case of Young's double slit experiment, all those points at which a crest falls over a crest or a trough falls over a trough, if you join all those points, then this particular line is known as anti-nodal line. And all those points at which a crest falls over a trough or a trough falls over a crest, then if you join all these points, then this line is known as nodal line. So if you extend that anti-nodal line and extend up to the screen, then the point at which this anti-nodal line will cut on the screen or will join on the screen, you will be getting a constructive interference or bright fringe. And the nodal line, if you extend the nodal line up to the screen, then the point on the screen at which it will meet, you will be getting a destructive interference. So Young's double slit experiment is an example of wave front division. So in this case, you can see that the same wavefront which is originated from a real source of light is divided by these two pinholes S1 and S2. So these pinholes S1 and S2 behaves as virtual sources of light. And the second example is the amplitude division. You can the same diagram. This is a diagram of interference in thin films. The same diagram is this one. In this case, what happens when a ray of light, this is a ray of light, when a ray of light is incident on the surface of an oil film, then what happens? From the point P, some portion of the light ray is divided, some portion of the light ray is reflected, and some portion of the light ray is refracted. So the portion which is reflected, it is directed towards BN, and the portion which is refracted is directed towards BC. Again, at the point B, some portion of the light ray is reflected and some portion of the light ray is transmitted, or you can say some portion is refracted. From the point D, again, some portion is reflected and some portion is refracted. So from the same source of light, you are getting two reflected rays R1 and R2. One ray you are getting directly, and another ray is you are getting by traversing the path B, C, and D. So from the same source of light, from the same light source, you are getting two reflected rays R1 and R2. So since these two rays are originated from the same source of light, therefore they will be of the same frequency. whatever change in the source uh, in the source will be there, they will going to repeat in the light range R1 and R2. So they will have the same phase, and since they are traversing approximately same path, because the thickness of the film is very small, and therefore they will be almost in same phase. So you can say in this case, in this example, you are getting two reflected rays from the same source of light. That is why uh, this is an example from partial reflection and refraction. You know that in this example, the same light ray is divided into two rays from partial reflection, because some portion of the light ray is reflected and some portion is refracted. So at this point B, the same source of the same ray is divided. Some portion is reflected and some portion is refracted. So from the same source of light, you are getting two rays, and from due to the phenomena of partial reflection and refraction, and that is why this particular, in this case, you can say that division of amplitude is going to occur, because you can say that 50% of the intensity is reflected and 50% of the intensity of the light ray or is transmitted or refracted, you can say. So amplitude is divided. That is why this is an example of amplitude division. Now we have to discuss this particular in detail also. This is in your syllabus, interference in plane parallel thin film. What we have supposed that S is an extended source of light, and a light ray SA is originated from the light source S. S is an extended source. You can suppose that it is sun. So S is an extended source of light, and from the extended source of light, a light ray SA is originated, and it is incident on the surface of an oil film. This is an oil film, or you can say this is a glass. So uh, this may be an oil film. This may be a soap film, so a soap bubble, you can say, so, or a glass. So a light ray SA is incident on the surface of an oil film, and at the from the point A, it is partially refracted and partially reflected. Hello, students.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Are you getting what I am explaining? Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, I continue.
Excuse me, sir.
So yes.
Sir, please explain the nodal and anti-nodal topic once again. I was not
Okay,
able.
I will explain. I will explain in the last. Let me explain firstly this interference in thin film.
Okay, sir.
Yeah. So I was explaining this phenomena of interference in plane parallel thin films. This you must have seen that if there is a water droplet, or there is a water droplet on the there is a oil droplet on the surface of water, and if you view that oil droplet at various angles, then you must have seen colored fringes, and you must have seen a band of different colors, or you must have seen if you observe a soap bubble at different angles, then you must have seen colored fringes or colored bands. Those colored bands are obtained due to the interference phenomena, due to the division of amplitude. So the same thing we have to discuss. The same thing is kept in your syllabus, and what is the theory behind that? This we are going to discuss in this case. in this case, what we have assumed that there is an oil film or soap film which is on the surface of water, and this one is air. So the bottom medium is water and the upper medium is air, and we have supposed that this is an oil film or soap film, and a light ray which is originated from an extended source of light S is incident at the surface A, and from the surface A, you know that for every material, not every material, this is the property of every material, that it absorbs some amount of light, it transmits some amount of light, and it reflects some amount of light. And that is why the transmittance, the reflectance, and the absorbance is equal to 1. So, keeping that thing in mind, if we suppose that the absorptivity of the medium is very small, so we can say that from the point A, some portion of the light ray is reflected along the direction of R1, and some portion of the light ray is refracted along the direction of AB. Again, this is the interface of a denser medium and a rarer medium. So again, there will be phenomena of reflection along the direction of BC and refraction along the direction of T1. And at the point C again, there will be the two phenomena. The light ray will be reflected along the direction of CD, and it will be some portion of the light ray will be refracted along the direction of R2. So from the same source, from the same extended source S, what we are getting two rays, R1 and R2. So since these two rays R1 and R2 are originated from the same source of light, and if we suppose that the thickness of the film is very small, therefore they are nearly traveling the same distances. So if they are originated from the same source of light, and since they are traveling approximately same distances, therefore we can say that they will be of the same frequency, of the same wavelength, will be polarized. If they are polarized, then they will be in the same state of polarization. And since they are traveling approximately same distances, then we can suppose that they will be approximately in the same phase. So all the conditions of coherency, all the conditions of coherent sources will be satisfied for these two rays R1 and R2. Therefore, we can say that these rays R1 and R2 are the coherent rays, and the distance between these two rays are very small. Therefore, they will be in a position to superimpose to each other, and due to the superposition of these two rays R1 and R2, what we will get, if we observe from this place, then we will get interference pattern. And since this light source S is an extended source of light, what we have supposed that this is a white light source, this is sunlight, therefore we will get colored fringes here. This you must have observed in your real life. But if we replace this colored source from a sodium lamp, an extended source of light, a monochromatic, an extended monochromatic source of light, then at this place you will get dark, alternate dark and bright fringes. But in the if you are using a sunlight, if you are using sun as a source, then at this place you will be getting colored fringes. So as I have discussed that for determining the conditions of maxima and minima, in previous lecture we have discussed that in order to write the conditions of maxima and minima, the two requirements which we must have. What is the two requirements? We have discussed that uh, constructive interference will be obtained at those points at which path difference is an even multiple of half wavelength, and destructive interference will be obtained at those points at which path difference is an odd multiple of half wavelength. So in order to determine the conditions of maxima and minima, or conditions of constructive and constructive and destructive interference in this experiment, or for this case, what we have to do, we have to firstly determine the path difference between the rays R1 and R2. So for determining the path difference between the rays R1 and R2, or you can say the two interfering rays, what we do, we will do some construction. The first construction which we do, we will draw a normal from the point C to the ray R1, and this normal is Cn. Oh, and we have drawn another normal from the point A to the ray BC. Okay, so you know that if this is angle of incidence I. Okay, this, are you able to see my cursor? Hello.
Yes, sir, we
Yes,
are
sir.
able to see.
Yes, yes, sir.
Okay, okay,
Yes,
okay.
sir.
So in order to determine the conditions of constructive interference and destructive interference, what we have to do, we have to firstly determine the path difference between the two interfering rays. So if you see the path traversed by the rays R1 and R2, what ray R1 is traversing, what path this ray R1 is traversing, it is AR1, the path which ray R1 is traversing, it is AR1. But the second ray is traversing the path AB, then plus BC, and then CR2. Okay, what is the difference of the paths of the two rays? The difference of the paths of the two rays lies AB and BC in the film, and this AN in the air. Because if you see beyond this particular, beyond the point N, then the two rays are of equal length. So the difference of the path lies before the point N. Therefore, if we write the path difference between the two rays R1 and R2, then it will be path ABC. Path ABC means AB plus BC in the film. So AB plus BC. But since we are concerned about optical path, so in order to determine optical path, what we do, we multiply the real path. We multiply the real path by the refractive index of the material. So what we have done, we have multiplied this path AB plus BC by the refractive index of the soap film or the oil film. So it will be mu times AB plus BC and minus this path AN in the air. Okay, so the path difference is AB plus BC in the film and minus of AN in the air. So now what we have to do, we have to determine the values of AB, BC and AN by using simple geometry, and then we have to put the values of AB, BC and AN in equation 1, and in this way we will get the path difference between the two interfering rays R1 and R2. What we have supposed, that the thickness of the film is small t. So how we will get this AB? You know that if angle of refraction, if the angle of refraction is R, if this angle is R, therefore this angle will also be R. And since this is, so if you take this triangle, if you see this particular triangle ABM, then this AB, what you know and what you have to determine, you have to determine the value of AB, and what you know BM is T. So what is the relation between hypotenuse and perpendicular? The relation between hypotenuse and perpendicular, it is the relation sine. So AB is equal to BC, and okay, this is not hypotenuse. If you are taking this particular angle, and this one is of 90 degree. Therefore, this will be base. So the relation between base and hypotenuse will be a that of cos. So cos r, you can write what will be the value of cos r. Cos r will be base upon hypotenuse. So it will be bm upon ab. So bm upon ab, bm upon ab. Cos r is equal to bm upon ab. And you know that what is bm? Bm is t. So ab is equal to bc, comes out to be t upon cos r. Similarly, if you take this particular triangle A and C, A and C, and this angle is of this angle is I, and this one, since you have drawn a perpendicular on line AR1 from the point C, therefore this will be of 90 degree. So what you have to do, you have to determine you have to determine the value of AN, and AN, you know that AN, and this AC you can determine. AC you can write AM plus MC. AM plus MC. So what will be the value of AN? AN will be AC sine I. And this AC, at the place of this AC, you can write AM plus MC. And AM you can determine if you again go to the triangle AMB, and if you have to find out the value of AM and you know the value of BM, so BM you know that T, and AM you have to determine. So what is the relation between perpendicular and base? It is a relation
Positive.
of tan, perpendicular and base, the
Sorry.
relation between perpendicular and base. So it will be that of tan. So AM you can write BM tan R, and MC you can write BM tan R. If you go to this triangle BMC, if you go to the triangle AMB, then AM comes out to be BM tan R. In the same way, if you go to the triangle BMC, then you the value of MC will again comes out to be BM tan R. So if you put these values, then BM you know that it is T. So it will be 2 BM tan R, and BM you know that it is T. Therefore it will be 2T, and tan R you can write sine R upon cos R multiplied by sine of I. And from Snell's formula, you know that mu is equal to sine I upon sine R. So at the place of sine I, you can write mu sine R. You know that Snell's law. Snell's law, you know that the refractive index mu is equal to sine of I upon sine of R. So at the place of sine of I, you can write mu sine R. So if you simplify it, then AN comes out to be 2 mu t sine square R upon cos R. And if you put all these values in equation 1, now you have calculated the values of AB, BC, and AN. And if you put all these values in equation 1, then you will get delta is equal to mu times T upon cos R. BM and AM you have this AC and BC you have calculated, it is T upon cos R, and this AN you have calculated 2 mu T sine square R upon cos R. If you simplify it, then you get 2 mu T cos R. Okay, then there is a Stokes treatment, and the treatment is that whenever there is a ray which is reflected from the surface of a denser medium, then it suffers a phase difference of then it suffers an additional phase difference of lambda by 2. So in this path difference which we have calculated from the geometry, we will add lambda by 2, and this lambda by 2 is due to the factor that due to the factor because this ray R2 is reflected from the surface of a denser medium, and this is known as a Stokes treatment, which is written over here. You can go through this. So the total path difference comes out to be the total path difference between the two interfering rays comes out to be 2 mu t cos R plus lambda by 2. Now what we have to do? we only have to apply the condition which you have written in the previous lecture. For determining the condition for constructive interference, what we have to do? We have to equate it to the, we have to equate it to even multiple of half wavelength. Matlab, we have to equate it 2n times lambda by 2. So 2n times, if we equate it 2n times lambda by 2, here 2n times lambda by 2, 2 and 2 are the cancelled out. Therefore, it is written here. This you can write 2n times lambda by 2. So if you equate it 2n times lambda by 2, so 2n times lambda by 2. So 2n times lambda by 2 is there, and if you take this term in the left hand side, this lambda by 2 in the right hand side, then what will happen? Lambda by 2 is common, and in the right hand side, what you will get? You will get 2n minus 1 lambda by 2. So in this way, you get condition for constructive interference, and it comes out to be 2 mu t cos r is equal to 2n minus 1 times lambda by 2, where n stands for 1, 2, 3, so far and so on. What is mu? Mu is the refractive index of the oil film. Mu is the refractive index of the soap film. Okay. T is the thickness of the oil film or soap film. R is the angle of refraction. Okay. And this you have measured from the normal, since this is measured from the normal. And N is the order of refraction. N, the values of N is varies from 1, 2, 3 to up to infinity. So for n is equal to 1, you will get first order interference pattern. For n is equal to 2, you will get second order interference pattern. Similarly, for determining the condition of minima, what you have to do? You have to equate this path difference to odd multiple of lambda by 2. Odd multiple of lambda by 2 means 2n minus 1, 2n plus 1 times lambda by 2. Okay, 2n plus 1. So if you equate this to 2n times 2n plus 1 times lambda by 2, then if you bring this lambda by 2 from the left hand side to the right hand side, then n lambda by 2 will be cancelled out, and in the right hand side you only remain with 2n times lambda by 2, and this 2 and 2 will be cancelled out. Therefore, in the right hand side you will get n lambda. So the condition for maxima comes out to be 2 mu t cos r is equal to 2n minus 1 lambda by 2, and condition for minima comes out to be 2 mu t cos r is equal to n lambda. Hello, students?
Yes, sir.
Yes, sir.
Yes, sir.
Is every point is clear? Hello?
Yes, sir.
Yes, sir.
Yes.
Okay. So the same thing. Hello? Anybody
Yes,
has
sir.
any problem?
Yes, sir, in polarization, you said they have to be same polarization. So
Same
what
state
happens
of
if they?
polarization.
Yes, sir. What happens if they are not in the same state of polarization?
If they will be not in the same state of polarization, then you will be not be getting a sustained interference pattern.
What,
Okay,
sir?
because in the conditions for sustained interference pattern, we have discussed that the interfering waves should be in the same state of polarization. If they are plane polarized, then all the waves, all the interfering waves should be plane polarized. If they are elliptically polarized, then all the interfering waves should be in the same state of polarization. Should be elliptically polarized. So if they are not in the same state of polarization, you will not be getting a sustained interference pattern. So for polarization, for getting sustained interference pattern, sustained means which do not vanish with respect to time. If you are observing the film at the same angle, then they do not vanish. They should remain with respect to time. With the variation of time, they should remain.
Okay, sir.
Yeah.
And sir, another doubt in the thin film parallel thin film experiment, the amplitude of the wave is different. So how will it affect the interference pattern?
The amplitude of the wave is different.
Yes, sir. The first
That
ray which
that,
is
that we have
emitting.
that, the article which we have discussed in the previous lecture. In that case, also we have taken different amplitudes, A1, A2, or A, B. So amplitude may be different.
Yes, sir.
Amplitude may be different. The things which should be same is the frequency.
Yes, sir.
The
But will
frequency.
it be like that the dark fringes are not particularly dark, or
Okay.
it is?
So in order to get good contrast in the film, the difference between the interfering waves, the difference in the amplitudes of the interfering waves should be as small as possible. Because at the points of minima, if the difference will be very small, then at the points of minima, you will get very small intensity. And at the points of maxima, you will get just double intensity, or above than the double intensity, some greater than an intensity greater than some amount from the double of the intensity, from the sum of the intensities of the individual waves.
Okay, sir.
Yeah.
Okay, sir.
So this is interference phenomena which we have discussed in a reflected light case. There will be interference phenomena for the transmitted light also, because we are getting transmitted rays also. As we have discussed this phenomena for the reflected light case, there are transmitted rays also. Uh, for the for that case also, what we the same thing, we will proceed in the same manner. The same geometry we have to apply. What we will consider that S is an extended source of light, and from this extended source of light, a ray SA is incident on the surface of an oil film, and from the surface A, from the point A, it is partly reflected and partly refracted. Since we are here concerned with transmitted ray, therefore we will ignore the reflected ray. Again, at the point B, it is partly reflected and partly transmitted. Reflected along BC and transmitted along BT1. From the point C, again it is partly reflected and partly refracted. Refracted along CR2 and reflected along CD. And from the point D, again there will be a reflected ray and a transmitted ray, or you can say a refracted ray. So from the same source of light, from the same ray SA, you are getting two transmitted ray BT1 and DT2. So you are getting two transmitted ray T1 and T2. And since the thickness of the film is very small and the two transmitted ray are originated from the same light ray, they will be of the same frequency. They will be approximately traveling the same distances. Therefore, they will be approximately in the same phase, and therefore they will be they can be treated as a coherent light sources, coherent light waves, and therefore since they are traveling in the same region of space, therefore they will be in a position to superimpose, and from the superposition of these two rays T1 and T2, we will be getting interference fringes. Now, what we have to do, we have to determine conditions for constructive interference and destructive interference. The geometry we will follow in the same geometry which we have done in case of reflected light ray. The path difference between the two light ray will be same. The only difference which will be there is the lambda by 2 which we have added, because lambda by 2 is added only in that case when a ray of light is reflected from the surface of a denser medium. And since we are talking about here about transmitted ray, then lambda by 2 will not be added. So the path difference will be delta is equal to 2 mu t cos r. So in order to determine condition for constructive interference, what we have to do, we have to equate it 2 mu t cos r to 2n times lambda by 2. So if we equate it to 2n times lambda by 2, then 2 will be cancelled out. 2 in the numerator will be cancelled out by the 2 in the denominator. So what we get? We get 2 mu t cos r is equal to n lambda. So condition of constructive interference comes out to be 2 mu t cos r is equal to n lambda. And for getting condition for destructive interference or minima, what we have to do, we have to equate this 2 mu t cos r to 2n plus 1 times lambda by 2, odd multiple of lambda by 2. So it will become 2 mu t cos r is equal to 2n minus 1 lambda by 2. 2n minus 1, you can equate it by 2n minus 1 lambda by 2. Only in this case, this n will vary from 1 to infinite. And if you are putting it 2n plus 1 lambda by 2, then this n will vary from 0 to infinite. You can write 2n minus 1 lambda by 2 or 2n plus 1 lambda by 2. The only difference between these two is that if you are writing 2n minus 1 lambda by 2, then n will vary from 1 to 3. Because if you put n is equal to 1, it comes out to be lambda by 2. If you put n is equal to 2, it comes out to be 3 lambda by 2. If you put n is equal to 3, it comes out to be 5 lambda by 2. Okay. And if you are putting it 2n plus 1 lambda by 2, then n will vary from 0. So 0 will give lambda by 2 in the right hand side. 1 will give 3 lambda by 2 in the right hand side if you are using 2n plus 1 lambda by 2. So don't confuse in this that we are using 2n minus 1 lambda by 2 or 2n plus 1 lambda by 2, because both will give odd multiple of lambda by 2. The only difference between these will be in case of 2n minus 1 lambda by 2, n will vary from 1 to infinite. And in case of 2n plus 1 lambda by 2, n will vary from 0 to infinite. Okay. So now if you compare the conditions which you have determined for constructive and destructive interference in the reflected light case and in the transmitted light case. So you will see that the condition for constructive interference which you have got in case of reflected light case is the condition of destructive interference in case of transmitted light, and the condition which you have determined in case of reflected light, the destructive interference condition, is the condition of constructive interference in the case of transmitted light case. So you can say the phenomena of interference of light in thin films, in reflected light and in transmitted light, they are complementary to each other. The condition which is for constructive interference in case of reflected light, it is the condition of destructive interference in the case of transmitted light. And the condition which is for destructive interference in the transmitted light is the condition of constructive interference for the reflected light. So you can say from these four equations, from this equation, and the two equations in this particular slide, that the conditions of constructive and destructive interferences in the reflected light case and transmitted light case are complementary to each other.
Excuse me, sir.
Yes.
Sir, why are we ignoring the Stokes treatment in the transmitted light case?
Okay. The Stokes treatment, go to that, let me go to that slide. Read the Stokes treatment. When a light traveling from a rarer medium gets reflected by the surface of a denser medium, then it suffers a phase change of pi or a path difference of lambda by 2. So in case of reflected light, this ray R2 is reflected from the surface of a denser medium. This is the surface of a denser medium. So it is reflected from the surface of a denser medium. This ray is reflected from the surface of a denser medium. That is why what we are doing, we are adding lambda by 2 in the determined path difference. But in case of transmitted light, we are not We are not concerned with the light ray which is reflected. We are concerned with the transmitted light. So since we are only concerned with the transmitted light, therefore we do not have to add that lambda by 2 due to the Stokes treatment.
Okay, sir.
Yeah. Now, what you have asked, some student have asked any question, and I have suggested that I will discuss it in the last of the class. What you have asked?
Sir, I
Yes,
antinodal and nodal part.
antinodal. Okay, okay. Let me go to that slide and then explain. Antinodal. For example, if this is a wave, okay, so you know that these points are known as what these points? These points at which you get minimum intensity or minimum displacement from the, if this one is representing the mean position, then the points at which you get minimum displacement from the mean position, what you say to these points? Nodes or antinodes? What you say? These are antinodes, and these points at which you get maximum displacement are known as
Nodes.
hello.
Sir, nodes.
Yeah. So that I have explained in case of that experiment, Young's double slit experiment, means the points at which a crest falls over a crest or a trough falls over a trough. If you join all those points, then then the line which you will make is known as antinodal line. When a crest falls over a crest, or when a trough falls over a trough, then this will be an antinodal line. And the points at which a crest falls over a trough or a trough falls over a crest, then that line will be a nodal line. So antinodal line is going to meet at the point on the screen where you get maximum intensity, and nodal line will go and meet on the point and on the screen at which you get the minimum intensity. So no antinodal line will meet on the screen at which point where you get maximum intensity or bright fringe, and a nodal line will meet on the screen at the point where you get minimum intensity.
So,
Yes.
in transmitted light, why we have equated maximum equation with n plus 1 lambda by 2 or not by n lambda?
In case of transmitted light, the conditions which I have dictated in the previous class, have you noted down that condition?
Yes, sir.
So just do that. Don't see the PDF. Just you have calculated in transmitted light case 2 mu t cos r is the path difference. Okay. So what you have to do, you have to equate it to, even for getting condition of constructive interference, you have to equate 2 mu t cos r to even multiple of lambda by 2. Even multiple of lambda by 2 matlab 2n times lambda by 2. So when you write in the right hand side 2n times lambda by 2, then the 2 in the numerator and 2 in the denominator will be cancelled out, and you are remained with the condition or the equation 2 mu t cos r is equal to n lambda. In case of transmitted light, the path difference will be 2 mu t cos r instead of 2 mu t cos r plus lambda by 2, because that additional lambda by 2 will not be added in case of transmitted light. So the effective path difference will be 2 mu t cos r. So you, for getting condition of constructive interference, you have to equate 2 mu t cos r to 2n times lambda by 2, and 2 in the numerator will be cancelled out by the 2 in the denominator. So the condition for constructive interference in case of transmitted light comes out to be 2 mu t cos r is equal to n lambda. And for getting condition of destructive interference, you have to equate 2 mu t cos r to odd multiple of lambda by 2. Odd multiple of lambda by 2 you can get by two ways. Either you equate it to 2n plus 1 lambda by 2, or you equate it to n minus 1 lambda by 2. When you equate it to 2n plus 1 lambda by 2, then n will vary from 0. And when you equate to 2n minus 1 lambda by 2, then n will vary from 1. Hello?
Yes, sir.
Is it clear? Let me take attendance, and then if any problem persists, then I will explain. Okay, Jasandeep Singh, during the
Present,
attendance,
sir.
during the attendance, you have to switch on your camera, and then you have to answer the roll call. Okay, so first one, Jasandeep Singh. Jasandeep Singh. Spars. Spars. Absent. Bhavini Singh. Pranjal Arora. Who is this?
Hello, excuse me, sir.
Yes.
Sir, Sparsh here. I was present. My mic was not turning on.
Okay. So next one is Pranjal Arora. Pranjal. Pranjal, are you there? No, Pranjal is not there. Next one is Rama.
Present, sir.
Vipin Chaudhary.
Present, sir.
Divyansi. Divyansi. Divyansi.
Present, sir.
Divyam.
Present, sir.
Divyam.
Present, sir.
Mohit.
Present, sir.
Shekhar Vasis.
Present, sir.
Sahil Jain.
Present, sir.
Arti Goyal.
Present, sir.
Vanshika Jain.
Present, sir.
Vidhi.
Present, sir.
Divan Sharma.
Present, sir.
Hiren Sahani.
Present, sir.
Gauri. Gauri
Present,
Chadha.
sir. Present, sir.
Sameer Chaudhary.
Present, sir.
Shreya Yadav.
Present, sir.
Sudiksha Sharma. Sudiksha. Sudiksha. Yes Kapoor. Yes Kapoor.
Present, sir. Present, sir.
Hardik Anand. Hardik. Vanshveer Singh. Sankeet.
Present, sir.
Ishita Agrawal.
Present, sir.
Neha Goyal. Neha.
Present,
Parth.
sir.
Parth Batra.
Present, sir.
Aditya Rajput.
Sir.
Satvik Chaudhary.
Present, sir.
Satvik.
Present,
Y
sir.
batch. Yes, Y batch. Lakshika. Lakshika Bhagat.
Present, sir.
Sagar Madhwa.
Present, sir.
Aditya Kumar.
Present, sir.
Prajwal Goswami.
Present, sir.
Shantanu Raj Chaudhary.
Present, sir.
Ojas Singh. Ojas. Naman Kataria.
Present,
Naman.
sir.
Yuvraj
Present,
Walia.
sir.
Present, sir. Yuvraj Walia present.
Ojas is present or not? Ojas? No. Naman is present. Kusagra Jain.
Present, sir.
Nikita Sharma.
Present, sir.
Pragati Mehra. Pragati Mehra. Pragati is absent. Vani Sharma. Vani.
Sir. Pragati mera present, sir.
Okay.
Sir, Pragati
Aruni.
mera present.
Okay, I have marked. Aruni.
Present, sir.
Hemank. Hemank Bhatia.
Present, sir.
Sudhanshu.
Present, sir.
Aryaman Anand. Aryaman.
Present, sir.
Dakshikant. Dakshikant. Rakshit Malik.
Present, sir.
Aryan Sarovar.
Present, sir.
Nibir Deka.
Present, sir.
Anshuman Garg.
Anshuman Garg present, sir.
Next one is Prapti Chaudhary. Prapti. Parth Bansal.
Parth also present, sir.
Anushka. Anushka. Dakshit Chopra. Dakshit. Not present. Bhavya Singh.
Present, sir.
Geetan Sharma. Geetan Sarang Gupta.
Present, sir.
Sarthak Gupta.
Present, sir.
Anybody else whose attendance is remained?
Sir, Jashandeep Singh is present.
Jasandeep, I have marked. Okay,
Sir,
yes,
Parth Bansal.
Parth, I have marked.
Sir,
Sir,
you have
only
marked
the
my Sparsh.
only the absentees are Bhavini Singh, Pranjal Arora, Sudiksha Sharma, Hardik Anand in X batch, and in Y batch it is Ojas Singh. Ojas Singh is absent. Ojas Singh, and then Vani Sharma is absent. Daksh Kant is absent. Prapti Chaudhary is absent. Anushka and Dakshit are absent. Geetan Sharma is absent. Rest students are present.
Excuse me, sir.
Yes.
Thank you, sir.
Sir, at the maximum intensity, it is called a node.
Maximum intensity anti-nodes and minimum intensity nodes. Hello?
Thank you, sir. Thank you, sir.
Sir,
Yes, yes.
will you please suggest one reference book other than textbook? I'm quite confused from that list which was provided by you.
You can follow the book written by Brijlal and Subramaniam.
Okay, sir.
Optics by Brijlal and Subramaniam, or Ajoy Ghatak. Optics by Ajoy Ghatak.
Okay, sir.
Thank you, sir.
And sir, which textbook to buy?
You can take a textbook written by Satya Prakash. Engineering Physics by Satya Prakash.
Sir,
Yes.
जो टेक्स्ट एंड रेफरेंस आपने लिस्ट में प्रोवाइड कराया था उसमें नीचे टेक्स्ट बुक ऑफ इंजीनियरिंग फिजिक्स पार्ट 1 एंड पार्ट 2 मेंशन है तो वो नहीं लेनी